Hello! In this video, we are going to prove the following theorem. Suppose G is a group and A is an element of G. Then for all integers m and n greater than or equal to 0, a to the power of m to the power of n is equal to a to the power of m times n. Now, since G is a group, this means that G is equipped with a binary operation. And G is closed under that binary operation. Associativity holds. G has an identity element, and every element of G has an inverse. Now, in regards to elements of a group, we define exponentiation as follows. If A is any group element, then a to the 0 is equal to the identity element of the group, and a to the n plus 1 is equal to a to the n times a, for all integers n greater than or equal to 0. And a preliminary result that we're going to use in proving this theorem is the following. Given any group element A, we have that a to the m times a to the n is equal to a to the m plus n for all integers m and n greater than or equal to 0. Okay, so now let's get into proving this theorem. To start out the proof, let's let G be a group with identity element E, and let's let A be an element of G. And from here, we want to show for all integers m and n greater than or equal to 0, this equality is true. And to show that, let's first give ourselves an arbitrary integer m greater than or equal to 0. And from here, we proceed by induction on n. And we're going to show for all integers n greater than or equal to 0, this equality is true. So let's start with the base case. In the base case, we're trying to show that this is true in the case where n is equal to 0. In other words, we're trying to show that a to the power of m to the power of 0 is equal to a to the power of m times 0. So let's start out by writing the left-hand side. Now, we know that any element of a group to the power of 0 is equal to the identity element. So in this case, a to the power of m to the power of 0 is equal to the identity element. But again, any element of a group to the power of 0 is equal to the identity. So we also have a to the 0 equal to the identity. But of course, 0 is equal to m times 0. So we're done. Through this chain of equalities, we have shown that these two guys are equal. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0, and we assume that this equality is true for that arbitrary integer n greater than or equal to 0. And the whole goal of the induction step is to show that this is also true for n plus 1. In other words, we want to show that a to the power of m to the power of n plus 1 is equal to a to the power of m times n plus 1. So let's start out by writing the left-hand side. Now, applying the recursive part of our definition, if we replace a with a to the power of m, then we get a to the power of m to the power of n plus 1 is equal to a to the power of m to the power of n times a to the power of m. But then, by the induction hypothesis, we know that a to the power of m to the power of n is equal to a to the power of n times n. But now, we're in a position to apply this rule. So, what we can do here is, we can add the exponents. So this gives us a to the power of m times n plus m. And we can factor out an m, so we get this. And we're done. Through this chain of equalities, we have shown that these two guys are equal. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. And so, this induction argument shows for all integers n greater than or equal to 0, this equality is true. And we proved that this was true for an arbitrary integer n greater than or equal to 0. Since m was arbitrary, this means we have shown for all integers m greater than or equal to 0, we have for all integers n greater than or equal to 0, this equality is true. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.